Morning, we'll start here. So we'll start with questions. Quiz, what is it, the 27th, like 5 days, this quiz, and I'll share part to do Friday. I think that should kind of work perfectly. So we're going to do that great after the end today. And then also Monday we'll further talk about chapter 2. He's going to get us into the next week class. So everything is time out well right now. Should. So you think the answer is always right? The answer we're not out and we'll keep going. All right, so let's do 15 first. So for 15, okay, what mass variant contains the same number of atoms as 3 grams of lithium? Well, key to this is the same number of atoms. This would be like saying, well, same number of moles, right? If you have the same number of atoms, it would be like saying you have the same number of eggs, it's the number of moles. So what we need to do is figure out how many moles of lithium we have right here. So remember, if you're not given moles, you're not given moles 99 times out of 100, the very first thing you should do is get moles. And this is the only way we get the moles anyway. So this right here, 6.94 grams of lithium in 1 mole of lithium. Now, we could add the step. We could add 1 mole of atoms, but then we're going to go the opposite. You know what? I'm going to do it the long way. Then 1 mole of lithium is 6.022 times 10 to the 23rd lithium atoms. I wish somebody want to close that door up here. I wish I had more room here.
Because now, I mean, you solve this and just change this to lithium to barium and then go back to grams, correct? Because we want to know what mass, same number of atoms. Well, now you just change this to barium. And then your 6.022 is going to go down on the bottom, 1 mole on top. So we'd be duplicating this. But the moles would be the moles, atoms would be exactly the same. So the long way then is take, I'm going to go up here with it. Now you could say, well, get that answer. So we've got 3 times 6.022 to the 23rd. When we divide by 6.94, the number of atoms we have is 2.60 times 10 to the 23rd. So now we have 2.60 times 10 to the 23rd barium atoms, right? It's the same. Now we would divide by 6.022 times 10 to the 23rd barium atoms in 1 mole. Then we could go 1 mole of barium to 137.33 grams. But look, if I had this all in 1 row, the 6.022 is on top, here's on the bottom, right? Same number of atoms, same number of moles. So we could shorten this up. I wanted to show you, I wanted to solve it the way the question kind of asked. Okay, 21. I feel like number of carbon atoms in a light. 21. If we have 1 mole, this is a mole of sucrose. So that's really 1 mole. If we have 1 mole, we have 6.022 times 10 to the 23rd molecules of C12H22O11. With a mole, we have 6.02 times 10 to the molecules. We would call it molecules. Everything here non-metals. Then we would go 1 molecule of C12H22O11. Every molecule has 12 carbon atoms. And hopefully if there's an answer there, it's going to work. Let me track to 17. Let me make a comment about 17. In 17, the same thing to do is get all 2 grams. Then you know. you can get all the grams. And to do that, 1 AMU is 1.66 times 10 to the minus 24 grams. The easy way to do this is to get all the grams. Either get all the grams, get all the moles. Gotta get all the moles of the gas. Grams or moles going to be the same thing. You have to, best thing to do is get all the units that are the same, correct? You can't say one than the other is smaller than another without converting everything to the same unit. I just convert all those to grams safely. So let's finish this up. So we left off last time. We converted grams to moles, moles to grams. We talked a little bit of what I'm going to say is language stuff. Okay. Remember, the solution, a mole, it doesn't matter if you're talking about a mole of potassium atoms or molecules. Here we would use the term molecules. If something starts a metal ion, we call it formula units or ionic compound. But it's all the same. If you just have atoms, you use the term atoms. If you have a bunch of non-metals together, you're going to hear the term molecules. If it starts with a metal ion, you're going to probably hear the term formula, but it's all the same. All right, all the same. Okay, so we went moles to atoms, molecules, or formula units, or we went moles to grams. Those are two conversions that we work with. Okay. Now, what we want to do is we want to be able to go backwards. We want to be able to look at some information and say, how do we get formulas such as C7H5O3S? And the typical way to do that is to have what's called percentage composition. If we know what percent carbon in the compound, what percent hydrogen in this compound, nitrogen, oxygen, sulfur, we can back calculate this formula. That would be a typical way to put you in the compound and get the percentage composition back. Well, what is percent? Percent means per 100. It's really what percent means. Percent means per 100. But you necessarily have a sample size of 100. No. If I said how many people, what percent of students in this room are wearing glasses? I used to do males or females, but I'm staying away from that one. Time's moving on. It's 2023, right? So I do that one. I do glasses now. Let's say one. So we don't have 100 students in the room. So it's not perfectly coming out to 100. So then we simply do a part, whatever part over the whole times 100. And we add percent. Right? If you don't have 100 in the sample size, You do what part our mentions here, wearing glasses, or the whole all the students here. Okay. So what is the percentage composition of aspirin? So we want the percent carbon, hydrogen, and oxygen here. Well, the first thing is, what is what I'm going to call the whole? The entire compound. We want the molar mass. So the whole is 9 carbons plus 8 hydrogens plus 4 oxygens. So that would be the mole mass. Let's do that. So we're going to have 9 times 12.01. We're going to do this in moles, so I'm going to put grams down. Plus, we've got 8 hydrogen at 1.01 grams and 4 oxygen at 16. Oops, need grams there. So if we grab our calculator, that's going to be how many grams are mole of the entire compound, or the mole mass. So we would have 9 times 12.01 plus 8.08 plus 4, 18.17. Maybe 0.7. Now we're just going to do the part carbon at 180.17, the part hydrogen, and the part oxygen. So let me zoom it out. So my percent carbon, I'm going to put way over here. My percent carbon is going to be my part carbon, which is 9 carbons. Over 180.17. We'll times that by 100 and we'll add a percentage sign. And so what is our percent carbon? We get 59. How many sig figs of this? Like with 4 sig figs. So if we do this to 4 sig figs, we get 59.99. All right, so we got 59.99% carbon. We'll box that in. 4 sig figs, yep, 4 on top, 5 on the bottom. So 4 sig figs. And we've got hydrogen here. We're probably going to lose a sig fig on this, but we'll do hydrogen next. We've got 8 hydrogens at 1.01 grams divided by 180.17 grams. We'll multiply by 100. We'll add the percent. This is going to get us 3 sig figs this time. So we are going to be at 4.48% hydrogen. Then there's 3 different elements in the compound, all to add to 100%. You could do the same thing for oxygen, but we can just do this. Percent oxygen is going to be 100 minus 4.48 minus 59.99. All of those units are percent. And if we subtract that out, I should have put percent on all of those. That's our percent. So that's just percentage transition. Part over the whole. Okay, with that now, percent transition can help calculate our formulas. So to do that, we're going to talk about here, which is calculating empirical formulas from mass or percent composition. So molecular formula is a multiple of empirical formula. Or said another way, empirical formula is the reduced simplified form of the molecular formula. No different than simplifying a fraction. It's no different than simplifying a fraction. If my molecular formula is C6H6, I would simplify that to get my empirical formula of CH, right? What am I doing? I'm really dividing both by 6. And CH is 1 or 1, or excuse me, 1, 1. So what can I do here? We're going to do here. I can simplify form. This would be divided by 4. And I get CH again. So notice these are 2 different compounds. These are 2 different molecular compounds, but the empirical form is the same. C4H6O2. We're going to divide by 2, and we're going to end up with C2H3O. Now, technically, in water, we could divide by 1, but we would do the same thing. We can't reduce this. Well, here's what we're going to do going forward. What we calculate first is the empirical formula. So going forward, we're going to calculate an empirical formula. We're going to know it's CH, and then we're actually going to calculate what I call a multiplier here, and we know that's a 6 in order to get to molecular formula. If I take my empirical formula, multiply it by 6 going the other way, I can get my molecular formula. If I multiply this by 4, going back the other way, I would go from empirical to molecular. If I multiply this one by 2, that's what we're going to calculate. In this one, it's still be a 1. Let me summarize this again. We always calculate an empirical formula first from the empirical formula, we're going to calculate this multiplier. And then from that, we're going to get the molecular formula. Okay. So here's a chess. Step for calculating an empirical formula. Get grams, convert to moles, divide all moles by the smallest. That should reduce whole numbers by that 6, 6, 4, no fraction, no hours, like 5.5 or 1.5. If that whole number ratios, make the whole number ratios, multiply all ratios by the least multiplier needed to whole numbers. Now, what the heck does that mean? So here's my step 4 clarification. If you come out when you divide them out and you get carbon 2.5, hydrogen 3, I can multiply 2.5 times 2. I got to multiply everything by 2. That's going to create carbon. You can go from 2.5 to 5, right? And then hydrogen is also going to get multiplied by 2. So we end up at C5H6. We're just creating whole numbers. And whatever we apply to our partial, we have to apply both. So 1.25 be 1 1/4, right? 1 1/4. So we're going to multiply by 4. And then we're going to end up with carbon 5 again. Because 1 1/4 times 4 is 5. And then we're going to end up with hydrogen. We got to multiply that by 4 now. And the last one, 1.33 is 1/3. So multiply by 3. And if we multiply 1 1/3 times 3, we're going to end up with 4 carbons. And if we multiply 5 hydrogen by 3, we get hydrogen. Okay, let's put this all together. So I'm going to put this all together. There are a couple ways to do this. I do it for all of them because later on we're going to solve similar situations, the same approach. Okay, using mass data. So we're going to be doing gram, not percent composition. It said determine the empirical formula for iron oxide. Now, iron could be 2 or 3. All right, iron can have an oxidation state or 2 or 3. It would give us 2 different formulas. Well, this consists of 34.97 grams of iron and 15.03 grams of step 1, get grams. We already have grams. Okay. Already have grams. Step 2, convert to mole. So we just take both of these grams, 34.97 grams of iron. I'll line these up. Well, actually, I'm going to write in. It's going to be grams of iron. One mole of iron. Here, 15.03 grams of oxygen. I'm going to go grams of oxygen. 1 mole of oxygen. And then hopefully this one memorized. Oxygen. 16.00, right? 16.00. And for iron, so look at that baby up right here for iron. And we're going to get 5.5. 5.85. We know that. Ranch out. And I have point. What we got here? 4 sig figs for everything, right? We're dividing 4 here divided by 4 there. Sig fig then. So I'm going to do this 4 sig fig, 6, 2, 6, 1. Mole iron. And this division here comes out to 0.9394. So that's step 2, convert to moles. Okay, we got everything in moles. Step 3, divide all those by mole. That's why I like to 6 pen colors or 4 pen colors. Trade with a person next to you. I'm going to do that here. The smallest moles is 0.6261, right? So let's draw a line. We're going to divide both by smallest, which is 0.6261. 0.6261. And we'll divide by the smallest. We get 1 mole of iron, but we get 1.5 mole of oxygen. Now we know for those compounds are whole number ratios. Or now we're looking at Fe. Looking at Fe1. O 1.5. Okay, so we're going to use step 4. I'm going to make these whole numbers. So step 4 is we're going to multiply both of those by 2, correct? And if we multiply those by 2, we're going to get our final answer of Fe2 3. And with that, we know this is iron 3 and not iron 2, right? This is iron 3 oxide. So if it was iron 2 oxide, it would just amount to be 1 to 1, right? So no, we've got iron 3. Okay. That's not too difficult. Just take some steps, right? We're just converting random moles, divided by the smallest, made them all numbers. Okay, let's do the next one on the next page. So on the next page, it says the empirical formula is C4 C for H9. So we know that's the reduced form. Molar mass is 114.3. What is the Becca formula? Well, here's what we've got. We know that, first of all, this is the empirical formula. We're looking for the molecular. So we know that we have this. We have C4, H9. We know your book, I believe, there's an N for this, I'm pretty sure. We got to calculate what this multiplier is to get the true molecular formula. Remember, this is simplified. Previously, we divided, correct? But then I said we could go the other way. So what we're doing this time is we're trying to calculate what this multiplier here is. Trying to calculate the multiplier so that we can go from the empirical formula to the molecular formula. So I know if I took this multiplied by 2, I'd get the molecular formula. So we're calculating this multiplier. Well, here's how you do that. This multiplier is like this. In the numerator, it's going to be the molar mass. Typically, that's going to be given. We take the molar mass and we divide by the empirical formula mass. Okay, and the empirical form of mass is this mass right here. That is the empirical formula. All right, so let's do that. Let's see, right here. So the molar mass is 114.3. 114.3 grams per mole. The empirical formula mass is going to be let's see, 4 carbons plus 9 hydrogens. Right? 4 carbons plus 9 hydrogens. And hopefully you got the memorized 12.01, 1.01. So we'll grab calculators and put that in there. So 4 times 12.01 plus 9 times 1.01. $57.1. So at this point, we know this is going to be, this has to be a whole number here. In this case, we get our multiplier to be 2. Well, our multiplier is 2. We have C4H9. So we get C8H18. Right, so we just multiplied this by, is our multiplier. Okay. Here's one with percentage composition. These are molecular formula. Now, again, there's 2 ways to do it. You might do it a different way. I'm going to show you the same exact technique because later on, you have to do the same technique. We have carbon, hydrogen, and chlorine. There's 3% here. They have to add up to 100. So my percent chlorine is going to be 100 minus 24.3 minus 4.1. And that is 71. 71.6 grams. Oops, I already put grams in there, so grams. The reason I put a D in there, I got ahead of myself. So 71.6%. Now, step 1 is the grams. Step 1 is to get grams. Percent means per 100. So we're just going to assume we have 100 grams. If we have 100 grams of this compound and 24.3% of it carbon, how many grams of carbon do you have in that 100 grams? 4.3 grams, correct? You got 100 grams sample, that's 4.1% hydrogen, 4.1 grams of hydrogen are in that sample, and 71.6 grams of chlorine. So we can just change these to grams, grams, grams. So that was step 1. Grams. Step 2, confirm all the moles. Convert all the moles. So I'm going to line them up here. So we'll line them up right here. We need to do 3 here. So we'll have enough room. We've got 24.3 grams of carbon. I'm just going to go like this for now. Come back and fill that in. 4.1 gram of hydrogen and 71.6 grams of chlorine. And 1 mole of carbon is going to be grams of carbon. 1 mole of hydrogen, grams of hydrogen, and 1 mole of chlorine, grams of chlorine. Twelve point oh one. 1.01, 35.45. Okay. Grams crossed out, of course. We're always canceling units. We get 2.023 mole of carbon. 4.06 mole of hydrogen. And 2. I did an extra stick fin, didn't I? It's not a bad idea to keep an extra number here. Usually I tell students to keep an extra sig here, but let's see what happens. Okay, so that's up to everything in moles. Step 3, divide by smallest. And the smallest is 2.02. Right, so I'm going to grab a different color. We'll divide the smallest. This 1 mole of carbon. 1 mole of chlorine. I'm going to put this number, it's going to be so close. Now you're going to know if it comes out to be like a 1.5 or a 1.33. This is out to be 2.00 or 2.01, but this is 2. So here we have so far. We got 1 carbon, 2 hydrogens, and 1 chlorine. We'll figure out this multiplier because we're given more mass. So this is going to be 99 grams per mole, which is given. Right? It's going to be given. We're going to divide by the empirical formula mass. Which is 1 carbon, 2 hydrogens, and chlorine. 1 carbon, 2 hydrogens, and a chlorine. Get us 49.98. Which means our multiplier is a 2, right? Equals 2. So our final formula is C2H4Cl2. This last problem, convert all these to grams, line them all up. You should be able to print this baby out. So on Monday, I'll put maybe this up. We'll be into chapter 3. You can do all the quiz now. Right? Do all this quiz. I think I'm just going to leave the deadline up there. It's 5 days, right? You should be able to pull throughout. So we're doing 1 through 25 now on quiz. That roll sheets we're at. And have a good weekend.